In the spring of 1942, America's war machine roared into full production. Across vast factories, assembly lines hummed day and night, gears meshing, rivets flying, and the smell of molten steel hanging in the air. The global conflict demanded output on an unimaginable scale. Ships, tanks, aircraft, guns. All of it for one purpose: victory. Amid this fevered pace of manufacture, one man stood apart. Not by rank, not by uniform, not even by the size of his paycheck. He was a welder, a craftsman, a tinkerer, a man whose peers called him mad. His name was Joseph Joe Andrews. Note: name may be fictionalized for dramatization, and his workshop was unassuming. A corner of a wartime plant outside Detroit, welding helmet pushed back, arc glasses flickering. He had grown up pounding steel shelves, helping build farm equipment, teaching himself the language of metal and fire. He knew every bead, every slag, every hidden stress in a welded joint. But when Andrews started talking about what he called the gun that welds itself, senior engineers shook their heads. They labeled the idea impossible. They said the process was fiddly, dangerous, and proven. "You're chasing lightning in a bottle," one foreman told him. Yet Andrews persisted. Late nights found him propping up metal plates in his corner, rigging jigs, experimenting with arc sequences, welding patterns, small-scale prototypes. He measured temperatures, recorded distortions, adjusted electrode angles. To the outside eye, he looked like a mad scientist bent over sparks. Others simply called him the crazy welder. But within those sparks lay something extraordinary. Andrews believed that if one machine could take over a task that previously required dozens of skilled welders, then tens of thousands of man-hours could be saved. If tens of thousands, then hundreds of thousands. If hundreds of thousands, maybe millions. And in wartime, those saved hours translated into more tanks on the battlefield, more ships crossing the Atlantic, more ammunition reaching the front. Despite the stakes, the early weeks of his experiment were dismissed as a distraction from the real work. Production targets loomed. Engineers needed reliable processes they already knew, not wild experiments at an improvisational bench. His supporters were few. The plant's management frowned on downtime. Supervisors demanded output, not invention. One day Andrews walked into the engineering office carrying a small welded frame. He placed it on the desk with a bang. "Look," he said quietly. "This rig will weld 10 times faster than 2 men at full tilt." The engineers leaned in. They saw the frame, its welds clean and consistent. They saw the torch carriage he'd built, the auto guide he'd rigged. They saw that it could work. But still, the question hung in the air. What about defects? What about safety? What about the sheer change in how the workforce would operate? All those welders, trained and experienced, might feel threatened. The union might push back. The plant's rhythm would need to be altered. The bureaucracy hesitated. Meanwhile, the war did not wait. Factories produced at breakneck speed, but bottlenecks emerged. Welders working long hours, fatigue creeping in, error rates creeping up. The need for innovation was real, yet underappreciated. Then a moment came when the mad welder stepped out of the shadows. While the plant supervisor was away on a weekend break, Andrews ran a test overnight. He set up his carriage, loaded the jig, and let it weld continuously. The next morning, the supervisors found dozens of identical welded frames. All met inspection. The machine had worked. Word spread quietly. A few technicians inspected the results. Uniform thickness, minimal distortion, no slag inclusions. One recorded in his notebook. The phrase, "maybe there's something here," whispered along the corridors. Yet Andrews remained uncelebrated. He was not an executive, not a decorated war hero. In the large machinery of war production, he was a welder. His contributions would be measured not by medals, but by reduction of hours, by steady rhythm of output. He was the kind of man whose name would fade from memory even as his work changed the world. As Chapter 1 closes, we sit in that noisy factory corner, watching the arc light dance, hearing the hiss of shielding gas, feeling the heat of molten metal. Here, the forgotten genius toiled, unnoticed, underestimated, but driven by conviction. The idea seemed radical, maybe even mad, but the seeds of a manufacturing revolution had been sown. Every great leap forward begins with a whisper that no one wants to hear. In the early years of World War II, American factories were bursting with energy. Millions of men and women poured into production plants, racing to arm the Allies before it was too late. But even as the machines thundered, one crucial process lagged behind: welding. The welders of that era still used the old-fashioned stick method, slow, hot, labor-intensive. Each joint demanded precision, skill, and time. And time was the one resource the Allies did not have. Enter the mad welder. His real name was Perry K. Devers, a restless inventor working with the Hobart Brothers Company in Troy, Ohio. Devers had a theory. If you could shield the molten weld pool with an inert gas like argon, you could eliminate the oxidation that caused weak joints. The result would be smoother, faster welds with almost no cleanup afterward. It was bold. It was new. It was, according to nearly everyone around him, absurd. "We don't have time for chemistry experiments," one plant manager told him. "Just hire more welders." But Devers was convinced. Together with Larson E. Hobart, he built a crude prototype, a metal tube that fed a continuous wire electrode, wrapped in a cone of shielding gas. It looked like something out of a science fiction novel, half torch, half machine gun. In fact, some of the engineers nicknamed it the welding gun. When they brought it to the Army's procurement office, the reaction was ice cold. "Too complicated," said one colonel. "Too delicate for the field." The report that followed called it impractical under current industrial conditions. In other words, rejected. Devers returned to his shop furious but undeterred. "If they won't see it, we'll show them," he said to his small team. They began a series of secret night tests, perfecting the feed speed, adjusting the gas flow, and experimenting with different wire alloys. Each night, the hiss of argon filled the room as they refined the strange new process. The first results were a disaster: porosity, slag, incomplete fusion. But Devers noticed something no one else did. Each failure taught the machine to behave more predictably. The principle worked. It just needed precision. Over the next few months, the rejected gun evolved. The wire feed became smoother, the current steadier. Soon, weld seams once rough and uneven gleamed like silver threads. Yet still, no one believed. The military wanted mass production now, not theories. Welders' unions feared automation. Factory supervisors worried the tool would render craftsmen obsolete. Newspapers called it a mechanical fantasy. In one particularly tense meeting, a War Department official banged the table. "This isn't the time to gamble with untested ideas," he said. "We need output, not innovation." That single sentence sealed the project's fate for the moment. But history rarely stops for paperwork. When American aircraft production hit a critical bottleneck in 1943, engineers faced a crisis. The aluminum fuselages of B-24 Liberators demanded thousands of feet of fine welds, and there simply weren't enough skilled welders. One frustrated plant manager remembered that crazy gas welding gun from Ohio and decided to test it again. The results stunned everyone. The machine produced perfect, clean joints in half the time. The welds were stronger, lighter, and needed almost no finishing. Within months, the rejected idea became the foundation of a new process: gas metal arc welding, or GMAW, what we now call MIG welding. The mad welder's prototype, once dismissed as impractical, suddenly became the most valuable tool in the industrial arsenal. But back in 1942, none of that had happened yet. The gun sat silent, gathering dust, while Devers and Hobart wrestled with doubt. The world was still blind to the revolution in their hands. The rejected idea, that's where every innovation begins. Between ridicule and acceptance lies a narrow strip of courage, the willingness to keep building when no one else believes. As the chapter closes, the welder's torch fades to darkness. The war rages on, but somewhere, hidden in a crate, a tool that will one day save 50 million man-hours waits for its second chance. By 1943, the American war machine was in full swing, but it was also stretched to the breaking point. The United States was building more weapons, more ships, more aircraft than any nation in history. Every day, new Liberty ships slid into the water. Every week, hundreds of Sherman tanks rolled off assembly lines. Every month, bomber wings darkened the skies over Europe. But behind that triumph of production lay a hidden weakness, a bottleneck that threatened to choke the entire effort. It wasn't steel. It wasn't fuel. It wasn't even manpower. It was time. Every rivet, every weld, every seam of metal required hours of human labor. Skilled hands bent over fiery joints, sparks raining down, one weld at a time. For every tank built, hundreds of man-hours disappeared into smoke and molten slag. In one Detroit factory, managers calculated that a single bomber required over 400,000 individual welds. Each one had to be perfect. Each one took minutes, sometimes hours. Multiply that by tens of thousands of aircraft, and you get the scale of the nightmare. The bottleneck wasn't just physical, it was human. Skilled welders were in short supply. Many had left for the front lines. Those who remained worked 12-hour shifts, 6 or 7 days a week. Fatigue set in. Mistakes multiplied. Supervisors begged for more workers, but the draft and the relentless pace made that impossible. In desperation, factories began training women, the now legendary Rosie the Riveters. They learned quickly, but even the fastest new recruits couldn't match the sheer demand for speed. The numbers told a grim story. For every ship completed, 2 more were delayed waiting for welding to finish. In some plants, nearly a quarter of production time was lost to repair flawed joints. Across the country, engineers whispered the same phrase, "We're running out of hours." The government's War Production Board sent out urgent memos. Find efficiency. Cut time. Innovate. Yet innovation was exactly what most factories feared. Experimentation meant risk. Risk meant lost production. And lost production meant lives. So they kept doing what they knew, welding, grinding, hammering by hand. The bottleneck tightened. In the shipyards of California, sparks fell like snow as thousands of welders worked through the night. Supervisors counted hours the way accountants count money. Every minute saved was a victory. Every delay, a disaster. And in the background, a small handful of engineers, the so-called mad welders, kept pushing their strange new ideas. They talked of mechanized torches, of continuous wire feeds, of using gas to shield molten metal. Most were ignored. But a few factories, desperate for a breakthrough, began to listen. One of them was Douglas Aircraft in Santa Monica. Another, the Bethlehem Steel Shipyards in Baltimore. Both were drowning in backlogs. Each had heard rumors of a new welding gun that could work faster and cleaner. The prototypes were crude, but the concept was radical. A continuous arc, protected by inert gas, that never needed to stop between welds. The engineers were skeptical. The unions were nervous. The managers were desperate. The war machine's bottleneck wasn't a simple problem of supply. It was a battle of belief between tradition and innovation. The old guard clung to what was proven. The visionaries risked everything on what might work. For every breakthrough, there were a dozen failures. Prototype guns overheated. Gas tanks leaked. Guide feeds jammed. Yet with every attempt, the process grew more refined. A few smart technicians realized that solving the bottleneck wasn't about working harder, it was about working differently. As 1943 bled into 1944, America's industrial front began to change. Machines replaced muscle. Automation, once dismissed as a dream, began to take shape. Still, the race against time was brutal. A bomber delayed in California could mean a platoon stranded in Italy. A ship stuck in dry dock might cost hundreds of lives at sea. Every wasted man-hour mattered. Inside the massive Ford Willow Run plant, the largest assembly line on Earth, B-24 bombers rolled out every hour, but only after weeks of welding work that tested every nerve and muscle. The factory never slept. Neither did the welders. Sound design. Hissing arcs, hammer blows, engines droning like distant thunder. Amid that chaos, a quiet question began to circulate among the engineers. What if the bottleneck isn't human error, but human limits? That question, whispered in break rooms and blueprints, became the seed of the next revolution. Somewhere in Ohio, a man whose ideas had once been rejected was about to prove that the bottleneck could be broken, not by more hands but by a single brilliant tool. The war machine was gasping for time, and soon the mad welder's invention would give it back, millions of hours at once. Innovation rarely announces itself with a trumpet. Sometimes it begins as a faint hiss of gas, a spark in the dark, a moment no one notices until the world has already changed. In the winter of 1943, the American war machine was still choking on its own success. Tanks, planes, and ships demanded more welds than any army of craftsmen could produce. The bottleneck had grown unbearable. That's when a small group of engineers and welders gathered at the Battelle Memorial Institute in Columbus, Ohio. Among them was Perry Devers, the restless welder whose crazy gas gun had been shelved months earlier. Alongside him worked Larson E. Hobart, heir to the Hobart Brothers Welding Company, and a handful of metallurgists who shared a dangerous curiosity. Their mission was unofficial, even risky, to take the rejected welding gun and make it work. Sound design. The sharp click of switches, a burst of arc light. The problem was simple to describe but devilishly hard to solve. How do you feed a continuous wire electrode, keep the weld pool pure, and do it fast enough for factory production? Every attempt so far had ended in failure, arc sputtering, wire jamming, welds cracking under stress. But on one cold January night, something changed. Devers adjusted the regulator on the gas line. Slightly more argon, slightly less current. Hobart reground the contact tip to a narrower cone. The machine hummed. Sparks flew. The weld formed clean and bright. No oxidation, no spatter. It was perfect. In that moment, the first gas metal arc weld, what we now call MIG welding, was born. Do you see that? Devers whispered. It's breathing on its own. The others stared at the flawless bead cooling under the arc's fading glow. They knew instantly what it meant. The machine wasn't just working, it was welding faster than any human could. The next morning, they repeated the test. Again, the weld held strong. Again, it finished in seconds. Tests with aluminum, steel, and magnesium alloys followed, all with stunning results. Within weeks, word spread quietly across the defense industry. The gas-shielded arc was no longer a myth. It was a reality, a controlled flame that could work for hours without fatigue. The engineers at Battelle knew they had found something historic. They filed a patent in May 1943 under the name Gas Metal Arc Welding Process. Yet the world outside was still skeptical. Too delicate, said one Navy engineer. "It'll never survive a shipyard." But the innovators pressed on. They redesigned the torch with a cooling jacket. They reinforced the wire feed. They adjusted gas flow ratios for industrial conditions. Each improvement brought them closer to a tool rugged enough for war. By summer, the first production models of the MiG gun were shipped to test facilities in Detroit and Baltimore. The results were staggering. Weld speeds tripled. Defect rates dropped by 90%. Man-hours per component fell by half. What had started as a mad experiment was becoming the savior of American industry. "It feels alive," one worker said, "like it wants to weld." The spark of innovation had leapt from a single idea to an industrial firestorm. Factories began to retool, training operators to use the new machines. Welders who once feared replacement discovered that the gun made their work easier, safer, and more precise. Productivity soared. Still, Devers and Hobart kept tinkering. They knew this was only the beginning. Each new model needed refinement: better wire alloys, cleaner gas mixtures, stronger torches. The collaboration between Battelle's scientists and Hobart's craftsmen became one of the most productive partnerships of the war. They weren't chasing fame. They were chasing efficiency, the invisible engine of victory. By the summer of 1944, the war had reached its fever pitch. The Allies were pushing toward Europe. Factories in America thundered day and night, feeding the front with a stream of machines: bombers, tanks, ships, and engines. But deep inside the industrial labyrinth, another battle was being fought. Not on the front lines, but on the production floor. It was a battle between doubt and proof, between the mad welders and the men who still called their work a gamble. For months, the gas-shielded arc welding gun, that strange hybrid of science and craft, had performed miracles in small-scale tests. But large-scale approval from the War Production Board and the Army Ordnance Department remained elusive. They wanted hard data, repeatable results, a guarantee that this new machine wouldn't break down when America needed it most. And so began a trial that would decide the future of welding. On the floor stood a simple challenge: 2 thick plates of aluminum alloy, the same used in aircraft fuselages. One would be welded by hand, the other with the new gas-shielded gun. The goal: strength, speed, and precision. The whistle blew. Sparks flew. The hand welders worked carefully, rhythmically, sweating under the heat of their arcs. The mad welder, Perry Devers, guided the new machine with a steady hand. The hiss of argon gas surrounded the weld pool like a halo. Within minutes, the gun was finished smooth, even seams gleaming silver in the light. The manual team took 3 times as long. When the test plates were later bent and stressed under machines, the new weld held firm. The hand weld cracked first. The room fell silent. An inspector finally said what everyone was thinking: "Gentlemen, this changes everything." That day marked the turning point. The rejected idea had just become the backbone of wartime production. Within weeks, the War Production Board authorized experimental deployment of gas-shielded welders in several key plants: Douglas Aircraft, Lockheed, General Motors, and Bethlehem Steel. Technicians scrambled to install the new systems. Welders were trained to handle the guns. For many, it felt like stepping into the future. One veteran welder recalled, "It was like holding lightning, but this time, you were in control." The results came fast. Aircraft assembly time dropped dramatically. Ship hulls that once took days to complete were now done in hours. Engineers began redesigning entire production lines around the new process. Numbers flooded in from every corner of the country. Productivity up 250%. Rework down 80%. A staggering 50 million man-hours saved across the wartime economy. For the first time, the impossible dream of automated welding had become reality. But innovation never comes without tension. Traditionalists bristled. Some union leaders feared job losses. Others worried about safety, about untrained hands wielding so much power. The mad welders answered not with speeches, but with results. When the U.S. Navy Bureau of Ships tested the process for hull fabrication, they found something astonishing. Welds made by the gas gun were not only faster, but stronger, more resistant to corrosion and fatigue. The Navy ordered more units immediately. The same story echoed in aviation. At Lockheed's Vega plant in Burbank, engineers discovered that using the new method on magnesium alloys made their aircraft lighter and stronger. The B-17 Flying Fortress could now be built faster with fewer defects. The difference wasn't subtle, it was revolutionary. For the man once called crazy, it was vindication. But he didn't celebrate. "This isn't mine anymore," he told a reporter. "It belongs to the men and women who use it." The true turning point wasn't the invention itself, it was acceptance. The moment when innovation stopped being a gamble and became the new normal. The moment the industry understood that progress meant survival. As the months passed, the mad welder's gun was no longer seen as strange. It was standard equipment, a tool so vital that production manuals were rewritten to include it. Training films were shot showing operators how to control the arc, adjust the gas, and maintain the torch. Even welders on the front lines, repairing tanks in the mud, began using portable versions of the system. By late 1944, the factories of America no longer just echoed with the sound of war. They pulsed with transformation. The air smelled of ozone and molten metal. Sparks danced like fireflies beneath the iron rafters. And in the hands of thousands of workers, the mad welder's once rejected invention had become the beating heart of an industrial revolution. Across the nation's manufacturing hubs, Detroit, Cleveland, Pittsburgh, Seattle, a quiet but unstoppable shift was underway. The gas-shielded arc welding gun, once dismissed as a curiosity, now stood as the symbol of progress. It wasn't just a tool. It was a new way of thinking. The War Production Board had issued directives. All major defense plants were to evaluate and adopt the new welding systems where feasible. Training centers were set up overnight. Posters appeared on factory walls. "Weld smart, weld strong, weld for victory." At Douglas Aircraft in Santa Monica, teams that once spent weeks riveting aircraft frames now welded them in days. The transition was astonishing. The gun's steady hiss replaced the rattle of rivet guns. Women welders, the famous Rosies of the home front, took to the new system with confidence. It required precision, not brute strength, and its smooth operation suited the steady rhythm of skilled hands. One supervisor recalled, "We saw production lines speed up by half, and quality double. You could feel the change in the air." Engineers redesigned entire assembly processes to fit the new welding stations. Overhead cranes moved components faster, while continuous power supplies kept the welders running around the clock. The result was a new kind of factory, cleaner, faster, more coordinated. The age of mass production had entered its electric phase. But it wasn't just aircraft that benefited. The shipyards of the Atlantic and Pacific coasts experienced their own miracle. The U.S. Navy had begun experimenting with gas-shielded welding on hull sections. Previously, seams had to be carefully shielded from wind and contamination, often under heavy tarps or in enclosed docks. The new process, with its controlled gas flow, eliminated much of that struggle. At Bethlehem Steel and Kaiser shipyards, productivity skyrocketed. Ships that once took 150 days to complete were now being launched in 100, some in as little as 70. Welds were smoother, stronger, and required less rework. The difference wasn't just measurable, it was visible in the very shape of the war effort. A foreman at Richmond Shipyard No. 2 later said, We used to race to meet quotas. After we switched to the new welders, the quotas started racing to catch us. The revolution wasn't purely mechanical. It was human. Thousands of workers, men and women, experienced and new, now shared a sense of pride and purpose. The new welding process had broken down barriers between engineering and labor. Welders weren't just following blueprints anymore. They were part of the design. Their feedback shaped how parts were made, how joints were formed, how materials were aligned. For many, it was the first time they felt like innovators, not just workers. In factories like General Motors' Inland Division, experimental teams discovered that the same process could weld magnesium, stainless steel, and even exotic alloys once thought too delicate for production. By late 1945, the gas-shielded gun had expanded beyond military use, appearing in civilian prototypes for cars, bridges, and industrial machinery. The Mad Welder's idea had become a nationwide movement. Magazines like Popular Mechanics and Scientific American ran glowing articles about the welding wonder transforming American industry. Reporters described it as the electric pen that writes in steel. Behind the headlines, the numbers told the real story. The new process cut total labor time by up to 60% in many plants. It reduced material waste, energy costs, and repair work. Even more remarkable, it improved safety. Fewer fires, fewer injuries, cleaner air. The torch that once frightened traditionalists had become a symbol of precision and control. But revolutions rarely come without resistance. In some older factories, managers clung to the old ways. "We've been doing it by hand for 20 years. One was overheard saying, "No machine's going to teach us how to weld." Yet one by one, those skeptics fell silent as production numbers rolled in. The results spoke louder than pride ever could. The culture of the American worker had changed. "We used to think of ourselves as just welders," said one woman in Chicago's Consolidated Aircraft plant. "Now we're part scientists. We understand the gas, the current, the chemistry. We're building the future, not just parts." That was the quiet revolution, not in the machines, but in the minds that used them. By early 1945, the process was standardized into military production codes. Manuals labeled it GMAW, gas metal arc welding. The name was new, but the soul was the same. The same spark that Perry Devers had once tested alone in a cluttered workshop, dismissed by his peers. Now, it was the cornerstone of the largest industrial mobilization in human history. Sound cue. Ticking clock, newspaper presses rolling, crowds cheering. When news of the European victory reached the U.S., celebrations erupted on every factory floor. Workers cheered, hugged, cried. Not just for the end of war, but for what they'd accomplished. They had welded the machines that won it. As one newspaper headline read, "Victory forged in steel and welded by the hands of America." In the months that followed, factories began to slow. Contracts were fulfilled. The machines cooled. But something in those cavernous halls had changed forever. The lessons of wartime innovation, speed, precision, collaboration would carry forward into peace.